All right, I'm just gonna make a quick video describing the assignment for this week. So it's called Stellar Evolution. Stellar just stands for star. So it's about stars and how they evolve over their lifetimes. The first thing is you should watch this YouTube video. About halfway through, it gets a little bit weird, but the first part is really good, just talking about different size of planetary bodies and then also stars. Every light you see in the night sky is a star, and they're all fairly close to us. They're in the Milky Way galaxy. Anything that and there are other things in the night sky, but you can't really see it with our eyes, but we can with telescopes. We can see other galaxies and stuff like that. But basically, every light is a star. All those stars are very similar to our sun. Not exactly the same, but similar. So they're making their own light, their own heat through fusion that we learned last week. So we learned about fusion last week where two atoms stick together, hydrogen in this case, stick together, fuse together, and as they do, they give off lots of energy. That energy travels through the star until it hits the outside, and then it's given off as light and heat and radiation, and that eventually hits the Earth, and that's where we get all our energy from, right? But then also all the stars are doing that on their own, billions of miles away, many light years away, and we're seeing those stars, that light from those stars too. So they're very similar to the sun, but they're not all the same. So after you watch that video talking about the different size of stars, it wants you to look at this HR diagram. It's called Hertzsprung-Russell. Those are the people who invented it. Basically, all these little dots are different stars near the sun. Okay. Now on the left side, this thing called luminosity. Luminosity is how bright stars are. Compared to L dot is the sun's brightness. So the sun's brightness is right here. So all these stars along this line are exactly the same brightness as the sun. And as you go up, you get much, much, much brighter. As you go down, you get much, much, much dimmer. And then on this is called the temperature scale. It is temperature and also has to do with color as well. Because the temperature of a star will tell you the color of the star as well. So when we look out, we can see the color of the star, and that actually tells us how hot it is, okay? But in this case, notice that the temperature goes to the left here. So the very cool stars are on the right side here, and the very hot stars are on the left side here, okay? So as you're analyzing that graph, notice all these dots are little stars, and it tells you how bright they are compared to how warm they are, how hot they are, okay? So I do want you to see that there's some shapes here, right? Some blobs together. From this, scientists can really determine how stars evolve because they can see where are most of the stars. So where do they spend the most time? And then how do they travel as they go? And what are they going to do? Because this helps determine what the sun is going to do as well. Okay, so please answer these questions before you get to the next part. Okay, so pause it, answer questions 3 and 4. All right, now let's go to the next one because the other one kind of gives you some of the answers, and I wanted you to kind of look at just plain old graph. Now we can add some color and some labels to this. So here is what we can discover from this. So you can see the main sequence here. You can also see lifetime in here, and you keep seeing these little 1.5 M, 1 M. So here's the sun, 1.5, 2, 6. So as you go this way, we're getting more and more massive. Okay, that's just how it happens, right? And then as you go this way, you can see they get smaller and smaller. There's these things called white dwarfs down here. There's the main sequence stars, which our sun is one. We have the giants, usually called red giants or yellow giants. And then we have the supergiants. We have the red giants over here, the red supergiants, Betelgeuse being one of them. That one is very bright, and I believe it's in Orion's one of the shoulders of Orion. And then we have some Rigel and Deneb. These are some blue supergiants. And then, yeah, as you go this, that's pretty much it. As you get too cold, you start to get like brown dwarf stars and stuff like that, which we don't know much about. So there's a lot we can tell from this diagram. There's some different questions I need you to answer, and then we'll go on to this next part. Click on this website if you can, because it'd be great if you can open it up yourself. Here's what it looks like. We're just going to do normal. We're just going to click, and here we go. So let's see some of the questions that we need to answer here. What happens to the sun size as it evolves over time? So this is the sun. Now I'm going to click play. I'm going to do it fast just so we can see what happens. We're talking about the sun here, 1 times the mass of the sun. I'm going to hit play, and you're going to see kind of what happens to the size of it as it goes along. Okay, now it's going to go very fast here, so it gets, and then zooms all the way down. Okay, so that's kind of what's happening to the size. I'm going to play it again. We're going to look at the temperature over time. Okay, I'm going to make it go a little bit slower. Sorry. So I'm going to have it go fast at first because it kind of takes a while here. And I'm going to slow it down because it does this curve very quickly. So I'm going to go normal here so you can see a little bit better what happens. So it's going up, 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 up. The temperature, though, isn't changing. Now all of a sudden it's going to hit this and very quickly go really, really hot. And then very, very quickly go very, very cold. Okay. Next part, we're going to see the brightness of the sun. So 1 would be the brightness, normal brightness of the sun. So as it goes along, it gets bigger and bigger and also gets brighter and brighter. You can see here it turns into a red giant, it's called. So the sun is going to become a red giant. And then it's going to zoom this way, not change its brightness. Change color, though, you noticed. So it is going to change color. It's going to turn blue, and then it's going to drop down and eventually become what's called a brown dwarf, or it's going to blow up and turn into a nebula. So this is what we think is going to happen to the sun. It's not going to happen for billions of years. As you can see down here, the sun's going to die billions and billions of years from now, so we don't have to worry about it. But as it does that, you'll notice that it's going to get huge. As we saw in the size, it's going to get gigantic. It's actually going to eat up I believe it's going to get so big, it's going to pass the Earth. So it's going to consume the Earth. And so we'll be dead at that point when it reaches all the way up there. But that's going to happen for billions of years, so you don't have to worry about it. You can see here how long it lasts in the main sequence. So it's in there for a while, and then it starts going to red giant for a while as well. It's doing that over millions of years, as you can see here. It stays in the main sequence by far the longest, though. And then it zooms over and basically turns into a white dwarf. All right, weight. So we can see actually the weight of the sun. So this would be 1 times the weight of the sun. So notice it's not really losing. Oh, it starts to lose weight a little bit even as it gets bigger. So it's actually spreading out and getting less and less heavy as it sheds some of the stuff. And then you can see here it gets very, very light as it zooms around and turns into that. So basically that's it blowing up in a sense. All right, so that would be a sun size. So please read those. By the way, it spends most of its time in what's called the main sequence. Now we're going to do it with the 2 times the mass. So I'm going to show you the different things for 0.2 times. So very, very small star. We're going to start with size. We'll press play here. So you can see it's tiny compared to the sun. So these are the smallest stars in the known universe here. So you can see actually these ones last a really long time. Many, many, many times more long than the sun. So the smaller the star is, actually the longer it lasts. But you can see it's going to get bigger and bigger. And it's basically going to do the same thing the sun did. So small stars basically do the same thing the sun did, but it takes much, much, much longer for it to do it. So they last a really long time. I'll do the same thing. I'm going to do it faster this time for temperature. because you can see kind of, and it's going to go basically do the same thing the sun does. Raise in temperature and then drop. Okay, brightness. Okay, and then we're not going to worry about time. Mass. So same thing, it's going to start losing slowly and then lose it really quickly. All right, now for the bigger stars, so we're going to do 40 times the mass of the sun. So these are the biggest stars that we know of in the universe. Let's start with just fast and see how that goes. Okay, so let's do it a little bit slower just to see what it's showing. So let's go back to size. So it's much, much bigger than the sun, and it gets gigantic like Betelgeuse, and then it actually supernovas. It blows up, and notice it turns into a black hole. So black holes come from actually the biggest stars in our universe. When they blow up into what's called supernovas, it's the biggest explosions that we know of, they turn into black holes. Okay, so let's look at temperature. All right, brightness. So notice that they start bluer, they turn into red giants, red supergiants, and then blow up. Okay. Okay, we'll do it for mass. They lose their mass very, very quickly. And then blow up. So there's a lot that goes into this. I learned about a lot of this stuff in college, and so it's not super important, but it's really interesting how stars evolve like this. And what this tells us is that the sun, there was probably a few other stars before the sun in our galaxy. I mean, in our solar system. So our solar system is probably multiple generations old because these big stars blew up and turned into smaller stars, which blew up and then turned into the sun, basically. So there's some stuff that you should be answering. And then finally, here is kind of how stars evolve. So I'll look at this one first here. So this starts at what's called a nebula, which is just basically a bunch of gas, a bunch of hydrogen gas. And over time, gravity pulls that gas in and turns it into a protostar and then into a main sequence star. So you can see here there's two different types. There's a low mass, medium mass, and then there's a high mass. Eventually, over time, that turns into red giants or red supergiants. And then the sun is going to basically shed off a bunch of this stuff and turn into a white dwarf. So it's not quite a supernova, but it kind of sheds everything out as the pressure from the heat just expands it outward. The high mass stars, those are the ones that are going to blow up basically into supernova. And then they can either turn into what's called a neutron star if they're a little bit less massive. They spin very fast, they're very bright and very hot. These are important for how we determine how far stars away are. And then black holes, or if the very, very big ones are going to turn into black holes. Okay, here's some more information about the stellar evolution here. Some words on there. And then I just want you to answer this last one here. What are 3 things you learned about stellar evolution through this? All right, hopefully that's helpful. If you do have questions, please let me know. Email me or meet me for my, what do you call them, office hours.